Hello guys, I hope you're enjoying your week and anticipating the weekend. And I see that a lot of people have started it early. About 10 people have started the weekend early. I guess you're not afraid of the year photographs, right? But okay, we'll see. So turn on the cameras, guys. We begin and we return to chain rule. Recall what we have been doing last class. We have decided that we only know very few species of functions. Just like in the aquarium, there are very few species of fish. We have the common polynomial fish, we have the radical fish, we have the involution 1 over x fish. Together with polynomials, you can create all rational functions. You see, by feeding the eel into the polynomials and the polynomials to the eel, you can create all rational functions. Remember why? Because a rational function requires only one division. So then we have the trigonometry fishes, which are the jellyfish here, and of course the exponential functions. Those are the only functions that we know, and those are the only functions we are able to differentiate at this very moment. So the idea we just covered is the following, is that when I take the derivative, remember we already did those exercises, the derivative is the derivative of the outer function and then multiply by the derivative of the inner function. And the analogy I used is that you fillet the outer fish, extract the inner fish and fillet it from the belly. Okay. Now today, oh, good guys, just very quickly, tell me what's the derivative of tangent of root of x, just to be sure that you still remember and you wake up. Quickly, derivative of tangent root x, type in the comments, cascade. Very good. 2 people write fast. Okay, good. Good. And this, I hope you understand how to do, guys. You should practice it, of course, at home. Today, we begin by trying to understand why that works. Why does that work? Why does the chain rule work? Let's try to understand the situation in the abstract. So what do we have? We have fx, which we can differentiate, and we have gx, which we can differentiate. The situation we're interested in is how to take the derivative of the composition function g f of x. How do I do that? You understand? I mean, of course, you might already symbolically know how to do that because we just practiced it, right? But that's, the word know is wrong. I told you how to do that and you carry the operation. By why is the operation correct? So tell me, guys, please, if you're dealing with a new type of derivative, where do you go? What's the first thing that you will think about? Once it's something new, you do what? Think of analogies, that's good. And you see, one person right away writes the definition of the derivative. That should be your instinct, guys, right? If it's not your instinct to go to the definition, then you do not understand mathematics, right? What is the definition? The definition is re-examining the very essence of the thing. Do you still remember what is the derivative? Do you remember what it is geometrically? Do you remember what it signifies in terms of velocity? If you do not, then you're already doing meaninglessness. So what is the derivative? Geometrically, you zoom in on a curve and you should be seeing a straight line. And the derivative is the slope of that straight line. Yes? So by definition, how was that slope discovered? So you begin by writing, what is this? This, if you prefer, let's call this function k of x. Let's label this as k of x. I'm not sure, I would have not done that, but I'm not sure, maybe it helps you. So it's k of x. What's the derivative of k of x by definition? So k prime x by definition is, one of the definitions is limit as z goes to x of kz minus kx divided by z minus x. Do you agree, guys? You understand the z, the x, doesn't matter. What is truly the derivative, guys? I'd like to remind you that you should think of that in absence of the letters. The letters are just supposed to help you see a picture. They should not be blocking your view. What is the derivative? In my mind, it is, again, I do use some letters here. So it's k of a box minus k of triangle divided by box minus triangle. And what happens? What happens is, of course, you should remember that the box is supposed to be like the triangle. You understand what I mean by that, guys? It's a number that morphs into another number, and you plug that number into the function and take the difference of the function that digests this number over the difference of the numbers. And I hope you remember why that's a definition of the derivative. That's a rise over run. That's why it's the definition of a slope. Yes? So this is what you should think. It should, even the k here is just because I don't know what I should draw. There is a function, it's a sort of like a meat grinder. It just processes and churns, or digestive system is what I tend to think. It digests the input. Good? So now let's try to understand what's happening here. So we have limit as z goes to x of kz minus kx over z minus x. That is a limit as z goes to x of, what is k of z? This is g of fz minus g of fx divided by, now guys, you all use smartphones, correct? And you notice that when you type a word, for example, you write th, and your smartphone is saying maybe what you're trying to write is the word the, right? Or you write thin, and it says, whoa, you're writing think, or think, or who knows something. It gives you suggestions, right? There is an autocorrect or a suggested word. So the machine is trying to predict what's to write there. Now, if you apply this machine to this expression, the machine would suggest writing what in the denominator. You understand? What would you expect to see in the denominator? What it seems that somebody is trying to do, and it should be fast. Okay. Z minus x is what's written in the denominator. Yes, guys? But what would you right away want to see in the denominator? All right. I'm gonna wait before I reveal. So, okay. I'm trying to have a poker face and not say what I think it is. Let's see. Come on, guys, a bit more. All right. All right, and it's pretty, I hope it means that you notice it, guys, right? So it is true that what you want to see here is f of z minus f of x. You want to see here, it's not, I'm not saying that's what you have, that's what you want to see. Do you understand? It's what I call wishful thinking, guys. If you wish for something very hard, it always comes true, at least in my experience. And in my experience, you always regret it. So do you see why f of z minus f of x? Because if I see this expression and I would like, let's say, let's suppress Alexandra, let's suppress Irina, and people that are not Alexandra or Irina will tell me what is this. What is this approaching? When I see this expression, I right away notice, ah, I know it. I know what it is. And it is what? A lot of you wrote f of z minus f of x. If you did not copy it, then you should know why. So what I circled in orange is a what? I hope you can see all my screen. I mean, it's a bit close to the edge of the screen, but you see all of it. You see the full board, correct, guys? And that orange thing is without approach, without anything, in short symbols. What is that orange thing in when you simplify it? Yes. Some people say f of x, the number that approaches x. Okay, we're getting a little closer. It is the derivative of, be more precise, just write the prime. It's, you can use a few symbols and you have it. A lot of you wrote f of z minus f of x. Why did you do that? Well, okay, that's part, but what is that orange thing that I circled? What is that going to be? F of z will approach f of x, correct? And that will be what? Look at it. What will that be? Well, the derivative, be precise, derivative of what? Of what at what? Do you understand? When you say derivative, you're being vague. Of what at what? John, where is your prime going? What you wrote looks like the derivative of the original function. It is not. All right. The answer is very simple. The answer is derivative of g at the point fx. Yes? Why derivative of g at the point f of x? Because, look at this, guys. Look at what's the box here. F is a differentiable function. So it means that it's continuous. Remember, differentiable means continuous. We did that both algebraically and geometrically. We see that differentiable means locally it looks like a line segment. So it's more than continuous, right? It's continuous and rather smooth, not crinkly. Do you understand me? And so what it is, look at it. It doesn't matter that z is going to x. What matters is that when z is going to x, it will make f of z go to f of x, because f is by hypothesis differentiable, which means it's continuous, right? So f of z and f of x will get closer and closer, like some of you noticed. And that makes it, look at it, what's the square here? Let me draw the square. The square is right over here. And the triangle is right over here. The square is right over here. Triangle is right over here. Are you with me? The square becomes the triangle. This is the derivative of g at f of x. If you understand this, guys, all of this class, that's why we are moving so slowly. All of this class is as simple as recognize that you're doing the same thing. Again and again and again and again, the same thing. So what I have here is that, of course, my original expression, look at it, there was a z minus x there, right? So I would look at it, this g of f of z minus g of f of x, it's this. Now what do I have on the numerator? I have to cancel out the f of z minus f of x, so I place them on the numerator. And on the denominator, I write z minus x. And now this approaches f prime x. And here we have then the product. Do you understand what we just verified? We just verified that the derivative of g of fx is the derivative of g in its belly f of x multiplied by the derivative of f. You see how we verified it, guys? Why the multiplication happened here? Because we can unravel the definition here of the derivative and recognize the definition of the derivative of g at a point f of x and the definition of the derivative of f at the point x. Good? Interesting to note, guys, is that if you sit or thought about probability, you know that you multiply probabilities, right? If you toss two coins, you know, and you ask for the probability for the coin two times, and you say, what's the probability the coin lands heads twice? So it's 1/2 times 1/2. The mechanism that makes multiplication work in that situation is the same as the mechanism that makes chain rule work. They are exactly the same idea that makes it work. You can, at least you can prove it using the same idea, right? You just unfold it. Good? Here is that thing written. I just chose x going to a. It's all the same idea. Clear? By just applying the definition and understanding it, guys, not being glued to x or h or to those letters, not being silly nominalists and bureaucrats, but understanding meanings of things and understanding that letters are just helping us carry the meaning, but not hiding the meaning from us. We can figure things very lightly. Of course, guys, you can do it another way. You can think of geometry and you can use a geometric analogy. Do you remember what is cascadeur? Do you remember the stand double? Yes? Remember that we could establish the derivative of product rule and quotient rule using stand double. And I will leave that pleasure to you. You see, here is the stand double again. And here I establish the chain rule using the stand double. So my advice is, of course, to try to do it on your own. And that would be easy because I think very few people imagine opening my notes, right? Based on the questions I have, what to study, what to do, I think nobody does it. Nobody opens the notes. Am I right? Now let's practice taking the derivative. What is a? The derivative of 4x minus x squared to the power of 100, and be quick. All right. So this one is not too bad, I hope, guys. It is just what? It's one polynomial that has eaten another. It's a sort of cannibalism here. So the derivative, yes, I see that a lot of you are writing correctly. So the derivative is 100 4x minus x squared to the 99 times the derivative here, which is 4 minus 2x. And we're done. Good. Now do problem number B. It's slightly more difficult. Problem B, please. Okay. This one is not too bad. Yes, guys, a bit annoying to even type. But let's write it down. So a derivative of b is cosine of e to the x times e to the x plus e to the sine x times cosine x. Good. Okay, so we're done with b. A much more annoying question is, no, I haven't yet given you the exam. My apologies for it. It's written, but it will be sent to you. You will have at least a week to do that, and it's due on the 29th of April. It's an exam that I think can be done in 2 hours, but I'm giving you more than a week to do it. Yeah, I will mention in class, and I will make sure that you have the exam. Don't worry. Yes, what was that? That was just somebody asking me about exams, being worried and nervous. But don't be worried about exams, guys. Worry only about one thing, right? Are you righteous? Do you know the material, right? Do you know in your heart that you know the material? Or if the answer is yes, then you know you should be spared. Yes, I will email it to you. It will be on email. I hate Blackboard, and I don't want to use it. All right, so C. What is the answer to C? If you don't want to write it, you can say easy or something, right? If you know the answer to it. Just want to gauge whether it would be something simple for you or not. Moshe, it cannot be because you suddenly lost division, right? I wait a little bit, guys, but if you want to stay after class, that's where we especially have a lot of time to do it slowly. Good? Yeah, yes. So let's do it together, guys. The idea is what? Probability, I forgot in which class I am. So the derivative of this thing is 1 over 2 root of the function. Yes. Times the derivative of what's inside, which is s squared plus 4 squared. And then here I copy s squared plus 4, multiply that by the derivative of the numerator by 2s minus reverse 2s times s squared plus 1. So it's just a simple quotient rule that follows chain rule. Good. If you prefer, it's all written in my notes. You can find it over here. Here it is, guys. If you want a better form of it, right? It's just what? Apply the derivative for the root, put whatever is inside, and then multiply by the derivative of the quotient. So it's just annoying. Now the derivative of d of tangent of cosine t, please. Okay, good. The derivative of tangent is secant squared, right? So it's very simple. The derivative here is secant squared cosine t times the derivative of cosine, which is minus sine t. You can write it this way if you want. Very good. Now help me with problem E. So E through H are slightly harder. Well, it looks nice. I don't know. What's the derivative, guys? Very simply, derivative of sine is cosine of everything inside, tangent e x squared, times derivative of tangent is secant squared e to the x squared, times the derivative of e to the x squared times 2x. Yeah? Good. Now, of course, guys, you know what I'm going to ask you to do next. It's f. Solve f, please. All right. And the answer to f is simple enough. Here it is, guys. Simply take the derivative of the root. The derivative of the root is 1 over 2 root 1 plus x e to the minus 2x, yes? Now, I can write the multiply to the numerator. The derivative of the inner function is simply e to the minus 2x. I took the derivative of x minus, I take the derivative of e to the minus 2x. It's just e to the minus 2x times minus 2. So it's minus 2x e to the minus 2x. And we are done. Now, guys, the next most annoying question of them all, and this is g. Take the derivative of g, please. Yeah, it's a bit hard to write, correct, guys? It's a bit annoying. Try a little bit, at least on your paper, we'll compare it together. Even harder to type into the text. So just write in your paper to the best you can, and we'll show you in a moment. Yes. You will check, you will self-check. All right, guys, let's do it together. So when I take the derivative, I will mark so that I don't get confused. I will mark with color. I'm gonna first get rid of the root. Yes, take the derivative of the outer function. What is the derivative of the outermost function? It's 1 divided by 2 root, and I copy everything on the inside, x plus root x plus root x. Yes, and then I write times. Then in parentheses, the derivative of the inside is 1 plus, now it's the derivative of the second root. I mark it maybe with blue. So the derivative of the second root, it's 1 over 2 root x plus root x. Yes. Times, because now it's the chain rule here, times the derivative of the inside is, it's the derivative of x is 1. And the derivative of root x is 1 over 2 root x. You see that? And we are done with this particular problem. As it happens, the next problem, guys, is actually easier. How do you take the derivative of root of x plus root of x plus root of x plus root of x forever? You understand the question, guys? How do I take it when this expression is written like what I wrote forever? Come up with a very simple formula. All right, how do we make it simpler, guys? Look at this expression. Why start taking the derivative right away? Do you notice something? If we call the full thing y, if the full thing is y, then do you see that y is contained within itself? Yes? All right, guys, do you see what happens? If this is y, then this here is also y. And so we have this equation. We have that y is equal to x plus y. So to be precise, look at it. This is y. So y is equal to the root of x plus y. You agree? And so what happens then? Then we see that I can solve this equation. This is just y squared minus y minus x equal to 0. I square and move everything to one side. You with me? This is a quadratic equation. So what is y? Y is, I can use quadratic equation. So it's minus 1, but this is beta. So it would be 1 plus or minus root of 1 plus 4x divided by 2. Since this looks like it's positive, I see that y of x is simply 1 plus root of 1 plus 4x divided by 2. And taking the derivative of that isn't very difficult. You agree? Because this is simply y equal to 1/2 plus 1/2 root 1 plus 4x. And so the derivative is obvious. It's just a very easy chain rule. Correct? You see, just because something has more terms and is infinite doesn't make it necessarily much harder. Actually, this question is easier than the one before it, the finite version. Right? All right, guys. And now we are ready to begin a new topic, a very difficult topic. And that's about no, not this one. Ah, interesting. Yes, I think in the morning I skipped something. So this is logarithms. So we'll talk about logarithms now, which is going to be hopefully something rather curious. But before we do so, right? Let me show you something that one of you sent me a few days ago. In fact, the person is in the class. I do not know why I find it so funny, maybe because I'm sadistic or because this class reminds me of that video. So I'll take 9 minutes and I will take back 5 once the class is over. If you cannot stay, it's up to you. Are you there, guys? Can you hear me? Yes? Is the communication good enough? I have no idea what's the logging. I mean, probably would be nice to restart. YouTube playback, I don't know. I think if I restart or something happened in the morning, it's fine. I will try to show it to you on Monday, on Tuesday, I suppose, right? All right. So let's see if you remember logarithms. Given a positive number a, multiplication by a with itself is simply represented in the numerator. So a times a times a is a cubed. So for example, 5 times 5 times 5 is 5 cubed. In general, if I multiply a by itself n times, I get a to the n. We know that with positive integers, there is this power rule. A to the n times a to the m is a to the n plus m, and that's simply keeping account of the number of multiplications that we carried. Yes? Now it's easy to understand that if you take a quotient a to the n over a to the m, the answer is a to the n minus m. Now why is that the situation? Is because the numerator a's cancel the a's in the denominator. Yes? So we have that this is a to the 4 minus 3, if it's 4 over 3. And if we want the rule to hold in general, we want a to the n over a to the m to be n minus m. We must have this interpretation of a to the power of a negative number. A to the power of minus k is 1 over a to the k. So for instance, a to the 3 over a to the 4, it means that only the solitary a on the denominator is the surviving one. Good? So it's 1 over a. Similarly, a to the 0, we already know why the answer is 1. Now let me ask you guys, what is 0 to the power of 0? Does it make sense? 0 to the power of 0. Now, why is it not existing? So some person says it's 1, but the answer is it doesn't exist. You see, why was the answer 1 in the previous situation? A to the 0 is a to the power of 1 minus 1, which is a over a, which is 1. But 0 to the 0, I cannot have that same process to define it, because 0 over 0 should mean nothing at all. I cannot divide by 0. Understand? So this is working for non-zero numbers. When I say a to the 0, I mean any number where I can have a cancellation to 1. So we also can observe that the following, that a to the power of n to the power of m is a to the product of the powers. So for instance, a squared cubed, it's simply a squared times a squared times a squared, right? Which is a times a times a times a, and altogether it's a to the 6th, which is a to the power of 2 times 3. Why is that happening in general? If it's an integer power, look at it, I can arrange the multiplication into a matrix, into a block. You understand, guys, where this is n columns and m rows. You see, this is a to the n times a to the n times a to the n. Do you see that? And when you just carry multiplication with a, and you just have to count how many times is a multiplied by itself. And you understand that it's simply how many rows? It's m rows times n columns. So it's n, it's m times n. It's 1n, 2n, 3n, mn. My explanation makes sense to you guys? You understand why I arranged it in a box? Because it has to do with area of rectangles. Same idea. Why is the area of rectangles what it is? It's because you're just counting blocks. A to the n to the power of m means that I have m rows of blocks of size n. So this is n, 2n, 3n, all the way to mn. Make sense? So for example, a squared to the power 3, it would be one row. So you see, if I had to represent, for instance, a squared cubed, that would have been a times a times a times a. Do you see that? That's the 3. And what do you see? You see that the answer is that I just multiply a by itself 3 times 2 times. Good. So those are a few problems. Now, similarly, we observed, I think before already, that the nth root of a should be represented as a to the power of 1 over n. Do you see why? Because the nth root of a means a number that when multiplied by itself, it means a multiplied by itself some number of times to get just simply a. So this means some number. This number is multiplied by itself a bunch of times, and you get n. So you can clearly see that if the power representation is x, then a to the x to the power of n is supposed to give you a. But if we believe that for all values it should be n times x, so x times y should be a to the x times y, that means that n times x should equal to the power 1, which means x is equal to 1 over n. You're with me, guys? I'm not saying anything too confusing. You see that? A to the power of a fraction can be defined as a to the 1 over n to the power of m. And even this can cause a sort of fuss. If you kind of just believe it, you can walk without noticing that you're walking very dangerously. You see, nobody told you that you're walking through the street dangerously and you will have a lot of false luck. And say sometimes it's good, and I feel bad that I point to the danger. Sometimes it's good to live your life and not realize that this life is very dangerous. Yes, so for instance, one issue is a to the power of 1 over n could have also been written, at least as a fraction. 1 over n can be written as the fraction k over kn, right? But that's very different from the, you see, so that's operationally, if that's how I define it, it's very, very different from a to the 1 over n. So my example here is trying to explain that, guys. So if I say take 5 to the power of, let's not use 5, let's use a better number. Let's say that we are we're going to take 25 to the power of 1/2, right? This simply is 5. You agree? That means just this means take square root of 25. Agreed? Take the square root of 25. Now, what is 25 to the power of, for instance, 3, 6? This is the same as 25 to the power of 1 over 6 to the power 3, based on the definition we gave over there. So that means take 6 root. Take the 6th root of 25 and cube it. Do you see what I mean now? Is that technically speaking, there are all sorts of dangers that you have to verify that you get the same result. It's not the same operation. Do you agree? Basically, although the fraction is the same, the operation is not. If I defined, and that's how it's defined, if I define a to the power of m divided by n to be the nth root of a to the power of m, if I do that as my definition, then you can see that you can run into certain things that you have to verify, certain things that you might, if you think about them, cause problems. Is that a fraction can be written in multiple ways, right? And here I wrote 1/2, and here I wrote 3/6. But if I write a fraction in a different way, I order a different sequence of operations. Yes, it could be, of course, 3/6 is 1/2, you agree? 3/6 is 1/2. You follow what I'm saying, guys? Right, so you can go through life and you can say, oh, 25 to the power 3/6, and you can say it's the same as 25 to the power of 1/2, and the answer is 5. But that involves much more clever thinking than you might have imagined. It just happened that you're lucky. It's happened that it works. But the schedule of operations is very different. If you say take 25 to the power of 3/6, it means take the 6th root of 25 and then take it to the 3rd power. Right? How do you know that it always yields the same as if you just simplify the fraction? It will, guys. You can prove it. It's a good exercise for you to deal with it. Another thing is if you ever get to complex analysis, which I wish you do, you have all sorts of interesting results, guys. If I asked you to find the cube root of 1, what would you write? Cube root of 1, what would you write? Don't worry, you don't have, you just what would you write if I asked to do that? No, just what would you write? Or maybe you think if I ask it, it means that you definitely have to write something weird. Okay, so a lot of you would have written the number 1. 1 is correct. 1 times 1 times 1 is 1 cubed. But in fact, there are 3 numbers that will, when you cube them, produce 1. So a cube root of 1, there is 1. There is minus 1/2 plus root 3/2i, where I is root of minus 1, and minus 1/2 minus root 3/2i. So you are lucky that you are spared yet with complex analysis. But if you take the 5th root of 1, you will have 5 solutions. If you take 10th root of 1, you would have 10 solutions. That's a property of a more advanced number system, one that is capable of representing 2-dimensional geometry. Right, so it's a different mechanism, and there is definitely a calculus on complex numbers. Now let's talk about. So this I will leave for you to think about, guys. You see, as it happens, let's say taking the root of 25 is the same as taking the 6th power, the 1/6 power of 25, and then cubing it. Will give you the same result. You just have to figure a way to verify that if you want. Now, here is a set of equations, guys. A set of equations, and you try to solve them if you can. So here we have 2 to the x equal to 4. What is x? Could you solve a, b, c right away? 2 to the x is 4, 2 to the x is 8, 2 to the x is 1. What do you think is x in each instance? You can just write them first number, second number, third number. Okay, 2, 3, 0. Thank you. That's fast. 2, 3, 0. Good. Now, the next column is what? The next 3, would you write what, please? Thank you. Quickly write the next column, guys. And then write the last column. The last column. Alessandra, you made one small mistake. Yes. John, same, you made a small mistake. Yes, so the answer is, here it is, guys. Here are all of them answered. The last is x to the power, x is equal to minus 1 over 7. Okay, and the reason you were able to solve it is that you just guess. It's just that you know which symbol works. Yes, it's a guess. Now, suppose that I asked you to solve this equation. 2 to the x is equal to minus 4. What would you write? 2 to the x is equal to minus 4. Okay. Now, guys, I'm sorry for having confused you earlier. Maybe we're introducing complex analysis. It's all very scary, right? You might start getting into this existential crisis of not knowing anything at all, or feeling like you know nothing at all. So, well, you know, what the answer is that if we are in real numbers, we think, okay, what can work? If I plug in 0, I'll get 1. So 0 does not work. If I plug a number bigger than 0, I think, well, 2 to the power of something bigger than 0, it doesn't work. It will produce a positive number. And if I plug in negative number in the power, it's just the reciprocal. 1 over 2 to a positive number. So there is no solution. No real solution, to be precise. No real number will satisfy this equation. Yes? No real number satisfies this equation, so this is meaningless. At least for real numbers, it is meaningless. For complex numbers, it's not. Now, suppose that I asked you to tell me what's the answer when you say 2 to the x equal to 5. What would you have written? All right, log base 2 of 5. Very good. Now, guys, do you understand what log base 2 of 5 means? It is nothing more than a name, and the name is suggesting that there is one thing that works and only one thing that works. Okay. The question is, of course, how can you establish that such things are meaningful? How do you establish that something like that is possible, that there would be something that works? It's easiest to do that for e to the x, because e to the x, we proved what it is and examined it and understood what e to the x means for all x's. Okay, and you can use the intermediate value theorem to do that, in fact. Right, so I will get there a little bit later. But when you say log base 2 of 5, you are just saying this is the number that if you place above 2, you will get 5. You haven't found the number, but that's actually what you do all the time, guys. Look at what happens, guys. Just let's look for a second and tell me, please, guys, what's the solution of this equation? X squared equal to 4. You would say x is equal to, well, 2 or minus 2 to be precise, yes? So x has two solutions. It's either 2 or it's minus 2. But if I said x squared is equal to 2, you would have written what solutions? why is there a log? No, it's x squared equal to 2, Safa, careful. If it's x squared equal to 2, you would have written what? Yes, it would be 2 root or minus root of 2. Yes? Now there is something very different about the number above and root of 2. Somehow root of 2 seems less known to us, right? Like you have a sense of what is 2, but what is a root of 2? It's just a number that when squared gives you 2. You follow, guys? It's just a name. It's a solution in everything but name. Without a calculator, until recently, I'm presuming now you all are able to calculate root of 2, right? I taught you how to do it in several ways, right? So you could, without a calculator, calculate what's root of 2. But in general, you know, it's just a statement of existence. So the same thing goes with the log. When I say 2 to the x equal to 5, and I say that x equals to log base 2 of 5, I am just, it's very similar in status to root of 2. I'm just saying there will be a number that in the number is unique, and if I place it on top of 2, I will get 5. Do you follow? It's a sort of Alice in Wonderland, a sort of black box. So this is the definition. A to the x is equal to b, means x is going to be written as log base a of b. And you should think of it as just saying, if you place this expression on top of a, you get b. You see, a is on the bottom and b is here. It's just a notation to say, place on top of a and you will get b. So it's very similar to that story in Alice in Wonderland. Do you remember that there was this vial, and it says on the label of the vial, drink me and be small. So you don't have to think about how this works. If the label is not lying, as soon as you drink it, you will get small. What's the inner mechanism? It's not known to you. Not known, at least at the very moment. All right, so let's practice, guys. Tell me what's 10 to the x. What's x if 10 to the x is equal to 3? What's the value of x? Okay. Good. So the value is simply log base 10 of 3. For b, it is what? Log base 6 of 2. For d, log base 5 of for d, you can actually you can do something better, right? Okay, log base 5 of 7, and for d, and what is log base 9 of 3? 1/2, right? So in question number 9, we can actually guess what the value should be. Place me on top of 9 and get 3. And you think, well, place 1/2 on top of 9 and you get 3. So here we have one value where we know how to calculate it fairly well. So log base 9 of 3, we imagine it will give us 1/2. Because if the number is unique, clearly 1/2 works. Clearly taking square roots should work. Good? So here we mentioned a little bit about the difference of explicit functions and not. Okay. So polynomials, if you remember, guys, are the functions I consider explicit because I see that the formula is displayed for me, because I understand how to process using addition and multiplication. Okay, so this means take a number, square the number, multiply the number by -5, and add 1 to it. I can see how to do this. Whereas if I say tangent of x, it's not directly clear how what operations, how the x is digested to produce the result. So some students don't wish to realize that, and so what do? They write something like sine of x squared over x is equal to sine x, because they cancel the x's. But that's meaningless. You understand? Sine of x means there is a function whose properties you don't know, and it's digesting x squared. When you divide the result by x, well, you know, what comes out of when you digest x squared within sine, what comes out is maybe very, very different from x squared. But in fact, do you know what comes out when you digest sine, guys? You can write an explicit formula. If sine is digesting x squared, do you know what's the actual operation that comes out? The actual operation would be x squared minus x to the power of 6 over 6 plus x to the power of 10 over 10 factorial and onwards. It's infinite, which you can establish on your own. So the digestion of what sine does explicitly to its input is very different from x squared. In general, sine of an input will be the input minus the input cubed over 3 factorial plus the input to the power of 5 over 5 factorial. Should be not 10 factorial, but 5 factorial. My apologies. And onwards. You understand? It's something that if you understood how to use calculus, you can come up with such formulas. Just like you understand what happens if you fit something in E. So sine of x is very different from, this thing is not meaningful. Sine times x, it's a meaningless expression. It's just a code for the operation to take place on x. Right, we know the explicit formula for e to the x. It's 1 plus x plus 1/2 x squared plus 1/6 x cubed and so on. That's the explicit formula by which the function exponential digested. You can even, in some people don't like to write the x on top. They just write this function this way, exp x, to try to, because you see, guys, if you think about it deeply enough, taking, let's say, 2 to the power of x, it's I don't understand what to do. If it's 2 to the power of 3, I do understand what to do. But if it's 2 to the power of pi, I don't understand what to do. You see, what do you mean place pi to the power of 2? What is happening? What sort of process is taking place? So it's a similar story for logarithms. But once we have a definition, we can actually get quite a lot of mileage out of it. You see, even though we don't know what the function is doing as a calculation, if we labeled it, we can see what properties that function shall have. So here is a simple comprehension check, guys. You see, first of all, log base a of x means place that logarithm on top of a, and the output is x. Here is a very quick comprehension check. What is 5 to the power of log base 5 of a smiley face? provided this is meaningful. All right, a few people see it. It's very simple, guys. Basic logic here. 5 is raised to what? Log base 5 of whatever it is just, this is just saying place me over 5, and that's what would be the result. You understand? It's like a sentence. This log is just like a mathematics or whatever foreign language, not English, just means place over to get. Place over this to get that. And the result will then be a smiley face. Clear? So, for instance, guys, of course you have to be careful. What is 5 to the power of log base 5 of minus 7? Yes, should be minus 7, except that log base 5 of minus 7 is meaningless. There is no such thing. You understand? There is no thing that you could place, because there is no number that would be the power of 5 that will give you a negative. It's not obvious. I mean, it might feel obvious if you kind of learned it at school. It's not obvious at all, right? Because it's not even obvious what it means to take 5 to some power. So using intermediate value theorem, you can prove that such things make sense provided the derivative of 5 to the x exists. For e to the x, it's the nicest function for which you can prove that any power is meaningful. So here are some properties. Log base a of x should mean I am the unique power of a that when placed over a gives x. And here are some properties that we should be able to establish. Log base a of m times n is log base a of m plus log base a of n. And log of the quotient is the difference of the logarithms. Now, are you ready, guys? I hope you still have a little energy in you. Do you? Because I do not. I'm tired. I feel pressure in my ears. Why doesn't it work? Why is YouTube so slow? All right. log base. So here is what we're going to try to prove. 1. So we have, how do I prove it? All I know about this expression is that if I place it on top of a, I will get m times n. So a to the power of log base a of m times n will give me m times n. Do you agree? And that is what? This is a log base a of m times a log base a of n. One second. All right, guys. One last effort. So a log base a of m times n. By definition, it's m multiplied by n. Do you agree? And this is simply m can be written as a log base a of m multiplied by a log base a of n. I can represent each of them this way. And what do I observe when I multiply those power? It's like a to the sum of the power. So I now observe that log base a of m times n is log base a of m plus log base a of n. Would you like to try to do number 2 this way? Yes. I think you don't. All right. Well, okay. It's today. It's, I'm not sure with you, but I realized what was happening is that I was cooked alive in here because the radiator was working. So yes. Goodbye. Take care. Enjoy your early weekend. Hopefully next time you come back, both the YouTube thing would work better, and yes, and we will have more energy.